Our last couple topics have been circular motion and gravitational fields. So obviously the logical thing to do is now combine those two things, which gives us orbits. So that's what we are going to look at next. Specifically, we're looking at the orbits of satellites, and by satellite I just mean a smaller mass that is orbiting a larger one. So for example, the moon going around us, so the moon is a satellite of the Earth. We go around the sun, so we are a satellite of the sun. Pretty straightforward. Now, we treat orbits as being circular. They're not, but we're going to treat them as if they are. So we're going to simplify it by saying that we're going to have circular motion, so our centripetal acceleration is going to be equal to v squared over r. And that acceleration is going to be equal to the gravitational force because of the larger mass on the satellite at the distance away it is. Yeah, so basically we're going to look for the value of g at the distance that we are from the sun, and that tells us our acceleration because it tells us the force that's being applied by the sun. And from earlier on, you'll remember that that's going to be gm over r squared. So we're just combining together the two equations that we've met earlier to do with circular motion and gravitational fields, because obviously they go together to give us our orbits. Now, the scientist we have to thank for the next law you're going to have to memorise is Johannes Kepler. And he did loads of work on the motion of the planets and describing their mathematical motion. And he's got quite a few laws. At the moment, we're interested in Kepler's third law of motion. So Kepler's third law of motion says that the square of the period of a planet is directly proportional to the cube of its distance from the sun. So basically t squared is proportional to r cubed. So the time period squared is proportional to the distance away cubed. Now, the full form, which will be in your data book, looks like this. T squared equals 4 pi squared over gm times r cubed. I've just pulled the r cubed out here so that you can see I've got my t squared proportional to, this is my constant of proportionality, and here's my r cubed. You could equally see the r cubed inside the brackets and on top of the fraction. I've just done it this way so you can see a little bit more clearly what's going on. And what I'm going to do is show you where this came from. Again, this is one of those things they could ask you to do. They would guide you through it step by step. But this one is, it looks a bit disgusting, but you have all the tools you need to do this, so it's not really that difficult. So, I haven't made it go step by step, never mind, right. We already have started with centripetal acceleration as being v squared over r, so that shouldn't be anything terrifying to it. If we then look at the speed, now I'm saying it's going around in a circle, and we know that speed is distance over time, and because it's going in a circle, the distance is 2 pi r, and the time is the time period for the orbit. All happy with that so far, I hope. So what I'm going to do is I'm just going to take this form of speed and put it into a equals v squared over r to come up with a new equation for centripetal acceleration. So it's v squared, so I'm going to square all of this, which would give me 4 pi squared r squared over t squared, and that's all divided by r. So if I do that, I end up with 4 pi squared r over t squared. And this is a new statement for my centripetal acceleration. Now, as I said earlier, that centripetal acceleration is caused by the gravitational field of the object that we're orbiting. So if I look at the acceleration caused by that field at that distance away, that's going to be gm over r squared, which is what we said earlier, and it's just a restatement of what we had before. Now I'm saying that these two things are equal to each other. So if I now rearrange, I can see that I've got a t squared and I've got r squared and r in here. So once I combine this together, I'm going to have my r cubed and my t squared. So once I just rearrange, I end up with t squared equals 4 pi squared over gm times r cubed. So this is where it came from. Centripetal acceleration, I just looked at what the speed actually means because it's a circle, plopped that into the acceleration, said, oh, well, I know the centripetal acceleration is caused by the gravitational field, so these two things are equal, and then I rearranged. and that just gives me that the orbital period is proportional to the root of the orbital radius cubed. And, you know, this kind of makes sense because if we have a look at Jupiter, it takes it a lot longer to orbit than it does for us because it's further away. So that should all make sense. If we want to check that Kepler was correct, we can take some data about the planets and plot them. So he says that t squared is proportional to r cubed. So if I plot a graph of t squared against r cubed, I should end up with a beautiful straight line that passes through the origin. So here we've just got 4 planets on it, and just taken the radiuses, cubed it, taken the time period, squared it, and I get the lovely straight line. So that's a way that we can prove that Kepler is right. And you should all be able to tell me exactly what the gradient represents. And I would love for you to have a little think about what we could use that gradient to calculate. So what could we find from that gradient? What thing that we might not know that we might want to know or might want to confirm could we get from that gradient? Have a think. Okay, so whilst we're on orbits, next thing we need to talk about are geosynchronous orbits or geostationary orbits. They're the same thing and the term often gets used interchangeably. Basically, it's an orbit where the satellite remains above the same point above the Earth the whole time. So it always stays directly above London, for instance. It's going to rotate at the same speed as the Earth is rotating, so it always stays above the same place. And in order to get that to happen, for it to stay above the same place, it's got to be a certain distance above the Earth. And if it's that distance above the Earth, it's in an area that we call the Clark Belt, which is pretty busy these days. So a reason we might want a geostationary satellite is for something like satellite TV transmissions. So I need the satellite to always be in the same place, so the satellite dish on your house always has to point to the same space. It doesn't have to track across the sky to follow the satellite around. It just points to the same place all the time. Mobile phone networks are another one. If we want to monitor, say, erosion of the ice caps, they're good for this. Looking at coastal erosion, looking at migration of animals, seeing where they go to and from within a certain space. Spying, weather, there's loads of use for these ones. Okay, now the important features of these orbits, they're going to have a time period of 24 hours. They will be 36,000 kilometres above the Earth's surface. I don't expect you to memorise this fact, but you will often have to calculate this number. So if you kind of have a feel for it in your head and you calculate it as being, you know, you've got a geostationary satellite and you calculate it and say it's, you know, 25,000 kilometres above the Earth's surface, probably made an error, so you know to go back and check. They would be circular, or we're going to assume they would be, and they would have to be above the equator, so they would be equatorial, and they would have to be going in the same direction as the Earth's rotation as well. Okay, hope that all makes sense. Yeah, orbits, easy peasy. Make sure you memorise Kepler's third, because remember we're going to start practicing all our definitions and things because they are an easy way to get marks and you just got to learn them. You have been warned. I will see you in class.